Welcome to lesson 7.5, and this is a lesson on parametric equations. We're going to divide this into 2 days. The first day we will talk specifically about parametric equations and going back and forth between parametric and rectangular. And on day 2 we will focus on a particular application of parametric equations. First, I want to just generally talk about the different types of graphs and equations that we've done so far. You're used to dealing with graphs that have a vertical distance, for example, on the left, time across your x-axis. Time is the independent variable, the vertical distance is the dependent. And it may be just like a parabola. You would have y equals a negative x squared something. Or you have still your independent variable is the time, but your dependent variable would be a horizontal distance, and that usually can just be a line, y equal x. When you deal with parametric equations, you have a unique situation that shows the vertical distance as a function of the horizontal distance. And so you have both of these components on the same graph. Now, if you've noticed, I've left off the time. Well, the time is configured into the equation. For example, it may be something like this, where at this point, or let's do this point, t would equal 1. Or at this point, t, the time would be 3 seconds, or 3, whatever the unit is. Or this, at this point, it's t equals 5. And as time progresses and advances, the function is moving in that pattern. This type of a situation allows us to give the time, the location, the direction of the function. It allows a lot more dynamics that you can do with this type of a function. We call these parametric equations. They express the vertical and the horizontal distance on one graph in terms of time. Now we call the time, it's the third variable, but we call it the parameter. And so we are going to write x. We have 2 equations instead of just 1. We have an x equation as a function of time, and we have the y equation as a function of time. The parameter sometimes is restricted, the time frame, sometimes it's not. If it's not restricted, as long as you yield a real number, you can have any time. You can have negative values if you're going back from a certain starting period. So unless it's restricted to start at 0 or within a certain block of hours or seconds or minutes, then it can be any number. You noticed when I drew this, I drew little arrows to show as time was advancing, the function was moving in this way. So we call that the orientation of the function. And you show that along the curve with arrows. So these graphs also have the little arrows. If you don't have an arrow to show me the orientation, then you will lose points. And you're leaving out part of your answer. You need to show me the orientation. All right, I'd like to do a couple examples. Let me scoot this up a little bit here. And I'm going to do these. There we go. Leave that there for you to copy that down if you would like to. Now I penciled this in because I wanted to write it in. Let me write it in a little bit darker for you. I wanted to restrict this one. So I'm going to restrict this function from 0 to 8, the time frame. Now the first example has x equals 3 times the parameter of time, y equals the square root of t plus 6. And so we're going to put both of these equations on a t-chart. I left off my y. So as the time goes from 0 to 8, as you can see that I've already written in because that's what the restriction was, we're going to go through and we're just going to plug in these values. So the easy one first, let's just take 3 times all of these values. That would be 0, 6, 12, 18, 24. Now go through and let's take the square root of each and then add 6. Now in some of these you can do right off the top of your head. The square root of 0 plus 6 is 6. The square root of 4 is 2 plus 6 is 8. All right, the rest of them aren't so pretty, but I can use my calculator and I can get an approximation. This is about 7.4. This is about 8.4. This is about 8.8. And then you graph the function as x on your normal x-axis and y as your normal y-axis, but you are incorporating the time. So I'm going to go ahead and plot this. Let's see, 0, 6, be here, 2, let's see, 2, let's do an easy one, 12, 12 to 8, let's see, that's 6, 7, 8, I know that one, 6 at about 7.4, 18 at about 8.4, 24 at about 8.8. All right, so I have this kind of a creature here. And there is my orientation. Okay, if I wanted it labeled, you could tell me this is where t is 2. You could tell me at 18, let's see, that was t was 6. And I can get an idea of where the graph is. Now I only wanted it to go from 0 to 8, so it has a hard start and a hard stop. Let's look at this function. Throw a little trig in there for you. This says x is 4 sine of 2 theta and y is 2 cosine of 2 theta. And this one is not restricted, but I know that when I put these values in for theta, you'll see that they'll start to repeat. So I'm only going to do basically one period, right? So if I put theta or pi in here, that's at 2 pi. And so I've gone one cycle. Let's go ahead and plug in these values. So 0 here would give me sine at 0, which is 0 times 4. It's usually 0. All right, pi over 4. If I put 2 times pi over 4, that's pi over 2. Sine is 1 times 4 is 4. Pi over 2 in here for theta. That would give me pi. Sine at pi is 0 times 4, 0. 3 pi over 4. 2 times 3 pi over 4 is 3 pi over 2, which is negative 1 times 4 is negative 4. Pi, 2 pi, sine at 2 pi is 0 times 4, again, is 0. Now we're going to do the same thing here with the cosine. If I plug in 0, that is cosine at 0, which is 1 times 2 is 2. Pi over 4 in here, that would be 2 times pi over 4, which is pi over 2. Cosine at pi over 2 is 0. You get the idea. Let me fill the rest of these in. One more. Pi, 2 pi, cosine at 2 pi is 1 times 2 is 2. Now, when I graph those, I am going to get a very interesting shape. Paper slide in here. All right, so let's go. And sometimes I physically, I don't know if you noticed I did this with the other one, I tend to cover up the first column so that I physically only see the x and the y, otherwise I start to plot other points. 0, 2 would be right here. 4, 0 here. 0, negative 2. All right, so I went from here to here. to 4, 0. Then I went to 0, negative 2. Came this way. Then I went to negative 4, 0. And then my last point was 0, 2 again. Oh, look at there. I have an ellipse. That graphed an ellipse. So it's, and you've done that before, okay? We've graphed the ellipse, but it hasn't been in this form. You're used to seeing it in another form. All right, let's try a few more notes I want to do, and then we'll look at some more examples here. I'd like you to add to your notes that you can have numerous parametric equations for the same rectangular equation. Now, rectangular equation, I'm speaking of, x and y equations. But you can have, you've got one regular rectangular equation. You can have numerous parametric ones. It depends on the time, on that parameter. They differ in their speed over that parameter of time. You can what's called eliminate the parameter to get from parametric to rectangular. So if you have a parametric equation, you eliminate the parameter, then you're left with the x and the y equation. I would like to go back and do the ellipse that we just did. So we're going to do example 1. We are going to go back to the b that we just did in example 1 again. And I'd like to focus on these two parametric equations, the x and the y. If we want to eliminate the parameter here, the parameter is not necessarily a t, but it's a theta. So we want to eliminate the theta. We need to move everything over here. We're going to divide by 4, so I'm going to have x divided by 4 is equal to the sine of 2 theta. Here I would have y divided by 4 is equal, no, y divided by 2, can't read, cosine of 2 theta. And now I'm going to use, to get to some of my trigonometric identities, I need to square both sides. So I'm going to square everything, perfectly legal, and do it on both sides. So now I have x squared, my orange is dying, how sad, over 16 equals sine squared 2 theta. And this would give me y squared over 4 equals cosine squared of 2 theta. And you know from your identities that if you have sine squared of 2 theta plus cosine squared of 2 theta, that equals 1. Okay, that's from your identities. The square, remember, sine of something squared plus the cosine squared of something equals 1. Well, now take these values and plug them, substitute them here into your inequality, or your equality identity. You're going to have x squared over 16 plus your y squared over 4 equals 1. Well, that's the form of the ellipse you're used to, right? This would be an ellipse, has a center at the origin. It has the major axis that is horizontal. It's going, A is 4 and B is 2. And if you look at the picture that we drew a few minutes ago in that other example right here, look at that. That is, A is 4 and B is 2. And you can have that equation in either this form or the parametric equation. So this allows you to also graph it on the calculator. When we come back in part 2, we will continue with some more examples. See you then.